today. But anyways, let's get things started. So today's topic is about calibration. After the calibration tutorial, you can actually continue and try to make this wireless thing working. But meanwhile, actually, the calibration, let me open that one. Good. So basically, just a reminder what we are talking about. We are talking about how to first find the sensor characteristics and then basically use those to find a better value for the sensor than what the just calculation gives. So basically we have lots of error sources on the system. And then, for example, linearity is one. No system is totally linear. And then the sensor behavior may depend on the environment, mechanical stress, measuring electronics. Well, that's a biggie. And then, of course, the time also changes the properties of any measuring system. So that's why basically there are also these some standard calibration or standard measures which are used to really calibrate a system. For example, if you want to calibrate a measure like that one, you would go to where? In France, right? No, not really. Well, that's where the standard meter is kept, but you would go to the Finnish VTT and their calibration services. But anyways, those services would be then, related to the source of the standard measurement standard. Okay, but anyways, we are not going to do it today. Basically, what we are going to do is just do a quick linear calibration based on a linear measure, and we can also basically take a look if our sensor is linear. And actually, I found really nice sensors. These are the best ones. Ultrasonic sensors that by default will give some non-linearity when you are close range. So we probably can actually see some funny results, and not only close range, but I would guess that there is also some skew on the signal on the far range. So I'm quite sure that we are getting a non-linear effect from this sensor. Okay, but anyways, that we already had earlier. Transfer function represents the relation between stimulus and response electrical signal produced by the sensor. Okay, normally the stimulus is unknown, but the measured response is known. But yes, an inverse transfer function is actually, when you have the inverse transfer function, then you have a calibrated system, if you think you know it. Okay, so there are several kind of ways. So for example, the easiest way, if you can somehow rely on the linearity of the sensor. For example, specifications give you, say, rough estimates about the, say, linearity. Then you basically, even a 2-point calibration might be enough. So basically what it does, it assumes that the device transfer function is a straight line, so first degree polynomial. So a offset constant b, and then you have this slope constant a that actually define the the whole calibration curve. And yeah, there's no magic on it. This is something you learned from the high school. So basically, if you have 2 points, then you can draw a line and just start calculating the values. So 2 points. Did I have the yeah, big S1, big S2, and the corresponding the values. You have the calibration points. So basically then you know that line actually follows A times S plus B. So that's the B, and then the slope is the A. Okay, that's simple enough. There's also another name for this kind of fitting of a line, finding the parameters. It's regression analysis. So simply do the measurements, plenty of the measurements here, maybe something like that, and then you can, in addition to the straight line, you can also fit, for example, parabolic polynomials or some other higher degree polynomials to the dataset, or try some exponential fit. But anyways, you can start doing the modeling, and you calculate your final result using the model. Okay, that's the main idea. Measure some data points and then make your model that follows your measurement data, and then just use that model as your calibration function. Okay, that was the theory. Simple. So let's see. I have the exercise, calibration of sensor. So basically, we actually have this nice ultrasonic ranging module, which works in a way that first you just send there a trigger signal, and then it should return echo, which is proportional to the time it takes for the for that acoustic signal to bounce back from the wall or something like that. Okay, good. So the setup is simple. Ultrasonic sensor. Should I do it left to right? So we have a measuring stick here, so that you can move a box or something like that. So that's something you can move. And then you have the ultrasonic sensor here somewhere, so that you have a reference point. It's up to you which reference point you choose. Is it the surface of that one, or the surface of the circuit board, or surface of something? But anyways, some reference point which defines you the zero, distance 0. Ha! Calibrated measure. Good. So then this actually takes just +5 volts and ground, and then the trigger signal input and echo output, and basically, well, those of course there are PSOC, and when you set the trigger, then at some point you will get the echo, which is directly proportional to this distance. Yeah, at least should be. So basically then, with this setup and just the LCD here, oops, not LCD, LCD. So what you would be doing is actually point pairs. The measured, okay, let's see. The basically the time. Actually time in counts. So fundamentally you would use some of the counters to count this time in between the trigger and a call pulse. And there you have the time 1, 2, time 3, time 4, and how many points you want to have there. Say 10 data points is quite a lot already. So you have the time in counts, and then you have the measured distance. D1, D2, D3, D4, D10. All right. Next step is actually to do the regression analysis. You can do it. You are familiar with Python. It has the regression analysis, so you can do it there. My favorite program anyhow is the MATLAB or Octave, either or. They work about the same. And there basically what you would do is to run okay. Oh, that was a smart idea. So you would run a function polyfit, where basically you have the vector, time vector and the distance vector, and then the polynomial degree. So with 0 you would get average. With 1 you will get the parameters for the line fit. For 2 you would get 3 parameters, meaning the second order polynomial, and so on. Simple to use, and I think there's also a way to also get the say confidence levels for those two. Anyways, my suggestion is to make the polyfit and then basically compare those values. Do you need higher order polynomials? Since when you think of this device, you have quite nice linearity in some region, and then on the in here you most probably get something like that, and on the other end you probably get something like that. So one path is very linear, but then close range well, that means what is the offset, meaning that you have a signal basically going in between of those. So even if you move it a little bit like that, it's about the same result what you're supposed to get. Distance from here to here doesn't change much when you are in close range, but then here it's more or less linear until it starts. It probably does start to go non-linear again, but that's something for you to check. Okay, good. But anyways, do this one and then some analysis of it. So compare this the measured valued with the modeled valued. I could actually here. Could show you a little bit of this comparison part. All right. MATLAB. Do I have a MATLAB here? that's a little bit tiny font there. Wait a minute, where was the preferences here? Fonts. Okay, in MATLAB, how to do the fit? So let's think of first of that we have the data set. I'll just put some numbers from my head. So the measurement times in counts vector, for example. Okay, just to make, say, some nice numbers which may or may not make any sense at the end. So I'm just making these numbers up. Add some, you know, the noise to the data by hand. Okay. 7. Oops. 8. 9,000 and 10,000. Okay, or 9999. Good. So those are my measured times from LCD, and then the distances. Corresponding distances would be, say, 10 millimeters, 20, 30, 40, 50, 60, 70, 80, 90, and yeah. So my assumption here is that I can set up this within 1 millimeter. And well, this is not a good example, but anyways, you could get that sort of results. So basically what it would look like is the data set, let's see, T and D, and let's put those in circles or cross X. Okay, so this is the data set. All right, and my question here basically is, can I make a linear fit to that one? What are the fit parameters, and how accurate actually my measurement was? So to give a vague idea of how good calibration actually is. You do not get better calibration than your measured data. Okay. All right. So that's the measured data set. First thing, let's just calculate the parameters for the first degree polynomial polyfit. Okay, I need to check what is the polyfit. Help on polyfit. Well, x, y, n. Yes, that was it. So always such that your x is your the measured value, and the y would be on the units you are would be the final product. Here my final product would be the distance in in millimeters. Okay, so it means that basically I need to just put there the let's see. Yeah, x is my count from LCD, and then y is the distance. And first degree polynomial. So those are the polynomial coefficients. So first, so basically these parameters are the highest polynomial order first. So my model for calibration of the system is that my distance is 0.0098 times the t what I'm calculating plus, or actually minus that, 0.8569. So that's the model. And next we can actually calculate what are the data points if we are using this model. So what kind of values we get from the model. So let's see, that will be a DDM, like DD model. We can actually do the polynomial evaluation with these parameters, par on data points, same measurement data points. There. There we go, and now we can actually plot that in here, TT, DDM, and mark those with these circles. Okay. So we can see there's a small discrepancy here. Well, actually this, when you plot it like that, you can actually start looking if there was a trend in the this curve, so that you would, for example, at the middle you will get lower values, at the ends you would have higher values, meaning that then you might actually go to the second degree polynomial. Rule of thumb on this method using polynomials: never use higher order than 5. Since you get higher polynomial orders, then basically you have just tiny bit of error on the highest degree polynomial, it goes haywire. So this method works only basically up to the 5th polynomial order. All right, so that's the difference. And well, we could also, well, the other one was actually straight lines. So what is the difference between that and straight line? Well, that's how easy it is to show. And then how about calculating the standard difference? Meaning, what is the difference between the measured and measured data points and modeled data points? What is the deviation of that error? Which would be more or less the same as our accuracy of the system based on this calibration data set, or inaccuracy of the system. So we calculate then the say difference. So we have the diff equals, so we have the data D minus DDM. That's the difference, just raw difference, okay? And then we just do the STD of DDIF, standard deviation of the data set and model. So in this case, the inaccuracy, expected inaccuracy of this data set would be 1.8 millimeters. So your calibration is roughly that close to the real. So plus minus that. All right. So we got the parameters. Parameter 1. I need more. Actually, I think I would need more digits to do that one. Just a moment. Can I actually see this one better here? No. No. Format, set output format. Yeah, those are the numbers what you can use on your calibration scheme on the microcontroller. Okay, now of course you need to do some floating point operations with these numbers, but you can actually also play with this, say what is the nearest fixed precision number, and do some magic that way. So you would use, say, let's see, parameter 1, okay, 1 over that one. So instead of using that as a scaling, you could also do okay, 102 as a divider for the counter value, for example. But then it would be nice actually if you then also check what happens if you have that 1 over 1 over 2 as one of the parameters, and do the that one again, and then difference again, and then std. How much you get? We get the same inaccuracy. Okay, so the rest of that is more like playing with this the accuracy of your result. How to calculate accurate enough value. So in this case, we do not need floating point on microcontroller, since we can do this kind of integer kind of tricks to calculate those. Okay, good. Anyways, so let's see, where's my history? Layout. Current for comment history. Dot. Oh, there. Okay. So not too many things that needed to do the calibration, the coefficients. So basically just the measured data sets, move that one somehow to the your favorite tool, then basically do the fitting, polynomial fitting, and then you can also calculate what the standard difference, so standard deviation of the data set minus the model, which gives you the accuracy of your calibration, and then basically just implement this calibration formula, or that inverse. This is basically the inverse transfer function of this sensor. Okay, not too much things to do. And how to do the higher order polynomials? Well, just go on the polyfit. Let's see, parameters, fractional second order. That gives you just one number more there, and then of course the DDM would be different. And then let's see how much this one actually helps. Not much. So first order and second order polynomial give you about the same accuracy. Of course you will get better fit with higher order polynomial, but you just need to basically think of if this fit is well worth of the cost, and is it really increasing the accuracy. In this case, absolutely not. But I could give another 5 credit course on the how to do the calibration, but for this course, this is enough. So that's why I have this the exercise, basically just that setup. You can change and measure the distance of the reflector within 1 millimeter accuracy. Make a calibration logbook, meaning, well, just a keep track on what the calibration of the measured data is. You have the counts on one and the one column, and the distance on another one. And basically just, then do some the fitting. The fitting itself is very simple. Then do the modeling using that fit to compare how good calibration you will get with that one. And yeah, so that's basically estimate the inaccuracy of your calibration. Then you basically have just the calibration coefficients, reminding that on this particular microcontroller it would be best to do the calculation on fixed point arithmetics, meaning the integer numbers. Maybe. Okay. And then modify your code so that it displays the calibrated distance. So that's the whole fifth exercise. You have the sensors and you have the PSOC systems. All right. So that's the story of the calibration.